Okay, let's go back and pick up section 2.5, which is all about continuity. So we talk about continuity at a specific point. A function is considered continuous at a point if the limit is equal to the function value. Easy enough. But that definition really requires three things. The function has to be defined at the point, the limit has to exist, and the limit has to equal the function. So if it fails any of these three things, then it's not continuous at the point. This is called the 3-point checklist. If it's not continuous, we say it is discontinuous or has a discontinuity. And let me make this a little smaller so it's not cut off the screen. So geometrically, you think of a function as continuous if you can draw it without picking your pen up from the paper. That's probably the definition that you learned back in pre-calculus. So let's look at example 1. It shows the graph of a function at which numbers is f discontinuous and why. So we need to tell why using one of those three things on the 3-point checklist. So I'm going to start looking from left to right at my example here. The first point of discontinuity I see is at x equals 1. So at x equals 1, it is discontinuous because f of 1 does not exist. 1 is not in the domain of our function. Moving on across from left to right, the next x value where I see a discontinuity is at 3. It is discontinuous at 3 because the limit doesn't exist. The left-hand limit does not equal the right-hand limit. Moving on from left to right, the next discontinuity I see is at 5. The limit exists at 5. The function exists at 5. 5 is in the domain, but the limit does not equal the function. So that is how I will expect you to justify your answer when you're telling me that a function is discontinuous at a point. There's the pretty answers. I'm going to leave that one for you to do, and of course I'll write it up and put it in the class notes. Now let's look at some that don't have the pretty pictures to go by. And I'll start just by writing down part A. It's x squared minus x over x minus 2. Now, knowing what you should know at this point in your mathematical career, you should know that rational functions have 2 points of discontinuity: vertical asymptotes and holes. So we need to figure out whether the point that makes a 0 in the denominator here is a vertical asymptote or a hole. So I see if the numerator will factor, and if it does, I see if I can cancel something. two numbers whose product is -2, whose sum is -1, minus 2, plus 1, cancel, cancel. So the graph of f of x looks exactly like the graph of the line x plus 1, except that it has a hole when x is equal to 2. So this is discontinuous at x equals 2 because f of 2 does not exist. Let's look at B. We have a piecewise function is equal to 1 over x squared, except when x is equal to 0. If x is equal to 0, it's equal to 1. So it exists everywhere. I just have to see if the limit exists, and if it does, if the limit equals the function value. Because 1 over x squared is continuous everywhere except at 0. So let's look at the limit as x approaches 0 from the left. Well, big bottoms go to 0, so as x approaches 0, actually the bottom's getting smaller and smaller. That would be if it goes to infinity. As x approaches 0 from the left, the denominator is getting smaller and smaller, so we're going to positive infinity. And since it's squared, it's going to positive infinity, even from the left. 1 over x squared goes to positive infinity. And for continuity purposes, the limit approaching infinity means that the limit doesn't exist. It doesn't exist as a whole number. It has to be a whole number in order for it to be continuous there. So we'll say the limit as x approaches 0 is infinity. That means we have a vertical asymptote there. Let's look at part C. So part C looks a whole lot like part A did. F of x is equal to, I'm going to go ahead and write x minus 2 times x plus 1 over x minus 2, as long as x does not equal 2. And it's equal to 2 if x does equal 2. Well, we already know that the function exists and the limit exists. Let's look at the limit as x approaches 2. As x approaches 2, this limit approaches 2 plus 1, which is 3, which does not equal f of 2. So we are discontinuous. Piecewise functions, usually the spot you're going to have to check is that place where the piecewise function changes. And the last one is the greatest integer function. You may not even know what that is. I'm going to bring up the pretty picture of it. It means the greatest integer less than whatever number you put in there. So f of 1.5 is 1, f of 1.9 is 1, f of 1.99999 is 1, until you get to 2, and then it becomes 2. So it has discontinuities at every single integer because the limits don't exist at every single integer. Okay. The kind of discontinuity illustrated in parts A and C is called removable. It's a hole. That means we could define the function in such a way, a new function in such a way that we could fill in the hole. The discontinuity in part B is called an infinite discontinuity. It's a vertical asymptote. The discontinuities in that last one, the greatest integer function, are called jump discontinuities. They happen when you have limits, left and right hand limits that do not equal. Now we can say a function is continuous from the right or continuous from the left. A function is continuous from the right at A if the right-hand limit is equal to the function value. Is continuous from the left at A if the left-hand limit is equal to the function value. So let's take a quick look back at this greatest integer function. It is continuous from the right at 1 because the right-hand limit is equal to the function value. It is not continuous from the left at 1 because the function value does not equal the limit. A function is continuous on an interval if it's continuous at every point inside the interval and continuous from the right at a left endpoint and continuous from the left at a right endpoint. So example 3 talks some more about continuity of the greatest integer function. Now it says to show that the function 1 minus the square root of 1 minus x squared is continuous on the interval from -1 to 1. Need a new sheet of paper. This is example 4. My f of x is equal to 1 minus square root of 1 minus x squared. So first thing I want to do is figure out the domain of this function. Well, in order to take the square root of something, the thing underneath the radical, the radicand, has to be greater than or equal to 0. So I just need to solve the inequality. 1 minus x squared greater than or equal to 0. Now it's tempting to subtract that 1 from each side, but you know you can't do that. This is a quadratic inequality. So let's write 1 minus x times 1 plus x is greater than or equal to 0. You could make yourself a little sign chart and figure out what that looks like. I'm just going to plot the zeros, minus 1 and 1. I know it's exactly equal to 0 at both of those endpoints. And now I think about, what does 1 minus x squared look like? Well, it has a negative leading coefficient and an even exponent, so it's a sad parabola. It's a parabola that faces down. That means it's positive between -1 and 1, and it's negative less than -1 and greater than +1. So since these numbers are in the domain, and we would be continuous from the right at -1 and from the left at +1, it is indeed continuous on the interval -1 to 1. It's continuous on its entire domain. Okay, I'm going to sketch one of these and then we'll leave the rest for you to do. And I won't do the easiest one. I'll do number 6. I'll leave myself a space to do number 5. I'll come down here and do number 6. So number 6 says it has discontinuities at -1 and 4. I have it's continuous from the left at -1. Continuous, not just from left. From left at -1, continuous from right at 4. So that means it has to, my sheet of paper, it has to exist, the function has to exist at 4. 1, 2, 3, 4. And the limit has to be equal to, from the right, from the left has to exist and be equal to the function value. It is discontinuous at -1 and continuous from the left at -1. It's continuous from the right. Limit as x approaches 4 from the right has to exist. Okay, I'm sure I misspoke, so let's say it again. The limit as x approaches 4 from the right of f of x has to be equal to f of 4. So that would look like that. Continuous from the left at -1. So the limit as x approaches -1 from the left has to be equal to f of -1. So I'll put it over here. And it's supposed to be continuous everywhere except for those 2 places. So I'm going to put a little line from here to here. Now your graph may not look exactly like that. You could have it do anything you want it to do as long as it fulfills those requirements. I'm going to leave the rest for you to do, and I'll work these out and put them in the class notes.